Hi, and welcome back to Engineering 255 Statics. This is the first part of the Chapter 4 video. We are going to introduce a new concept called the moment. The moment is a tendency of make an object to rotate. To calculate the moment, you can use a vector product called the cross product. So we're going to look at a cross product as well. We will show you some of the example how you can calculate the moment for two-dimension and three-dimensional cases. And we're going to talk about the important concept about the moment as well. So the objectives of this video is to understand and define moment and demonstrate how we calculate the moment for two-dimension and three-dimension cases. So first, let's just use a scalar formula to do the calculation to understand how we calculate the moment. If you apply a force to a wrench, and this wrench is connected to a bolt at O, and the distance from this point of O to the force is the distance of the D. And suppose your force is perpendicular to this arm here and here. You tend to turn this bolt counterclockwise, right? So go this way, which is counterclockwise. The tendency of the rotation after you apply a force about a point, which is the O, is what we define as the moment. The larger the force, the larger of the moment. The longer the distance, the bigger the moment as well. Sometimes we call moment as the torque, which probably you hear this in the physics, but they are actually meaning the same thing. So the moment is proportional to the force, is also proportional to the distance, and in the physics we call this one is the lever arm. Now let's simplify the graph as this one right here. You can see the bolt is located at the center of the circle O. And we're going to define a new property called the moment, and we use the capital N to represent the moment. You notice the N also have a subscript represent O, which is actually the rotation center, or what is the point is going to rotate about. So this O is a reference point or the reference axis. We said the moment is proportional to the force, so the larger of the force, the larger of the moment. It is also proportional to the distance, which is the d here, and we call this lever arm, so it's also proportional to this dA here. So a very simple scalar formulation, if you know the distance from this O and perpendicular to your force, then this distance d multiplied with the magnitude of the F is what we define as the moment. And notice the moment is a bold face, meaning this is also a vector. It has a direction. In the two dimension, this direction is going to be the direction perpendicular to the plane of the F and D. It always perpendicular to the F and D. So you can use your right hand rule to determine the direction. We're going to show you in the next slide, but just remember this moment is a vector. We define the direction of the moment as either the clockwise or counterclockwise. And clockwise will be negative if we write the answer. Sometimes you write negative, represent this as a clockwise. If you write positive, it's going to be counterclockwise. It's just a convention that we define the direction of the moment. Now let's suppose that you have a point of O, which is the object that you put in here, and you apply a force. And this force is not right at the point O, and is located at this point. So the force is applied at this point. How do we do the calculation to find out the moment? So again, the moment has to have a reference point, and this point at here is going to be the point of O, and it's proportional force and proportional to the D. It is important to identify the D actually. So the D is perpendicular distance. It's not like the distance from the O to the F. It is how much of the distance is proportional, is the distance from the point O to the perpendicular distance of O to F. So you can extend the F and such that you find the shortest distance. The shortest distance is going to be the perpendicular distance along the line of the action. Another way you can do is you can also decompose the force into two different components, which is X component and Y components. So look at this case again. You have a reference point here, and the force is right here. And you decompose the force of the horizontal, which is the Fx, the vertical, which is the Fy. So one goes to the right, one goes to the top, just like the bottom one here. We decompose the force with two components. Now, for the f of x, if we extend the line of the action, we find out the shortest distance of this point O to the line of the action is the distance of B. Similarly, if you look at f of y, you extend this force, and the distance from the O to the y is going to be the same as this distance, and that distance is distance of A. So you have two forces, they all have a different lever arm or the perpendicular distance. So you can find out the moment by summing these two together, but you have to also think about the direction of this moment. If you look at the f of x, think about this force. This force goes to the right, and the center is right at the bottom. So when you apply f of x, you're going to make this one turn clockwise. If you apply f of y, and this is your center of the rotation, it's going to force this to rotate in this way, which is counterclockwise. So the direction of the moment due to these two forces are going to be different. So if you want to find the moment with respect to the O, the sum of these two will be the sum of the moment. Again, what is the direction of f of y? The f of y go up, so it's going to turn counterclockwise. The f of x goes to the right, so it's going to make this one go clockwise. And we define counterclockwise as positive, so this is positive. Clockwise is negative, so this is negative. So you sum these two together, it's going to be the total moment of the force vector with respect to the reference point of O. And that is what this represents. This is a scalar formula, meaning over here, when you do this calculation, you're going to get a number, and this number is going to tell you the direction. If the number over here is positive, that means the moment is going to be counterclockwise. If this one is a negative, it's going to be clockwise. And that is how you do the calculation of the moment in the two-dimensional. Well, this seems like a very easy to calculate. However, if you are dealing with three-dimensional, sometimes it's not easy to find that, because the three-dimensional, you're not only going to have just one moment, you could have three different moments, because the dimension is not a two-dimensional anymore. Think about this. If you have two dimension case, and the force and the lever arm is on the xy plane, your moment is going to be perpendicular to the plane, which is going to be the z-axis. But if your force and the lever arm is in the x and z plane, then your moment will be on the y-axis. So you could have a moment if you are three-dimensional, then the moment could be the moment of x, moment of y, and moment of the z. So how do we deal with that? An easiest way is actually to use the cross product. When you have two vectors in two-dimensional, three-dimension, doesn't matter, use the cross product can help you to identify what is the net moment applied due to the force that has three different directions. And I strongly recommend that you use the cross product, and sometimes just looking at the picture won't give you the correct answer, but the cross product, if you do it correctly, will always give you the correct answer. Let's look at the definition of the cross product. A cross product is also called a vector product. It's very similar to the idea that we talk about the dot product in the previous chapter. The dot product is a scalar product, meaning the product of the two vectors is a number, but the cross product is going to give you a vector. You can use the right-hand rule by starting with a vector. So you use your right-hand rule, your thumb is going to give you the direction of the rotation, and that point up is going to be the positive direction. And you use the rest of the finger point to your first vector, and then you curve your finger to the second vector direction. So if you do A cross B, make your four fingers point to the vector direction of A, and then depends on where the direction of the B is. In this case, it's going to be counterclockwise, right? So you curve your finger counterclockwise to the vector of B. That thumb direction tells you this is a positive moment or negative moment. And if you do that, follow this picture, you will see the turning actually is counterclockwise. And that's why we define counterclockwise as the positive direction. This C here is the result of the cross product. And actually that is going to be our moment. And mathematically, if you have A vector, B vector, you do a cross product, this cross here represent the cross product, is going to be equal to the magnitude of A times magnitude of B times sine of theta. The theta is the angle between A and B, times the direction unit vector of u sub c. This u sub c in this picture is the z direction. Okay, it's the direction of the z. And this is going to be simply just give you a direction. So the magnitude is only just depends on A times B times sine theta. Let's use the Cartesian coordinate to understand how this one can be calculated. We're using the two-dimensional case to explain this. Let's say you have a vector f, which is in the x direction, and you have another vector which represents the y direction, and you do a cross product which is going to give you an I cross j, and that is going to give you a direction which is going to be in the z direction, and that is going to be the k direction. Okay, so if you cross the same direction vector, let's say I cross I or j cross j, you're going to get 0. and that is the definition. That is how you do the cross product of two vector. If I and j are parallel, meaning the two vector are parallel, you're not going to get any of the moment. But if the I and j are perpendicular, then you are going to get the result, which is on the third axis. Um, so how do you do the cross product if you actually have two vectors? Let's say we have a vector of A. The A had three dimension that has the x component, y component, and z component. Similarly, the B also have x, y, and z component. To do a cross product, you make a determinant and here put I, j, k, which represent the direction of each one of the direction. Then you write the A component and write the B component. The order matters. So A cross B doesn't has to be equal to B cross A. So you have to follow the order, put a component in the right order. And then you just follow this determine calculation, and you can find out what is the result of this cross product. I'm not going to go into the detail of this calculation. You're supposed to know how to do this one. If you don't, do some exercise to understand how to do this cross product. Now let's move on to the case how we use the vector formulation to do the moment calculation. So the definition, the formal definition of the moment with respect to a point of O is equal to the R cross F. R cross F. So F is simple to understand. F is just the force. And R, so what is R? The R is a position vector, where the position vector is from your reference point to the point that you apply a force. So if your force apply at this point, and the R is going to be from the original point here to where the force start. That is our R vector, and that is our position vector. And therefore, when you do this kind of calculation, you also need to mark the coordinate. That coordinate is going to be, oh, where the force start, where the force actually apply in the space. You need to find a coordinate of this point, and the R is going to be this coordinate minus this coordinate. That's our position vector of R. And once you have R position vector, you have the force in three components. You use the similar way that we told you in the previous slides. Put Rx, Ry, Rz, Fx, Fy, Fz, and Ijk on the top. Then you find out the determinant, and this is going to be your moment. This is going to be your net moment. And you will find out this moment is also a three dimension. It has I component, it has the J component, it has the K component. If you have I component, that means how much it will tends to rotate about the I axis, which is X axis. The K is how much you're going to make it turn around the Z axis. So it could possible that you have this rotation that rotate about three different directions as well. This should be, I think this should be positive at here, not the negative. So it'd be this much positive, this much positive, this much. Um, let's use some example to show you how can we do the calculation of the moment. In the first example, we are going to show you how to use the scalar method, the scalar formula to calculate the moment. The formula is that if you want to find the moment is going to be the force times the perpendicular distance of d. And if you have a multiple direction of the force, you can decompose the force into the f of x and f of y, and you sum them together, right? So you can sum the f times the d, and it depends on the component. So we want to find the moment of the force at the point of O. So your reference point is right here. The first thing we do is to resolve our force along the x and y axis, because this force is not a horizontal or vertical force, it's an angled force. It's angled with 3, 4, 5 triangle. If you decompose that, we have x direction of the force, which is equal to 100 times x is going to be 4 divided by the hypotenuse, which is 5. So we have 80 Newton go to the right. We can decompose the z component, well, not the z, the y component, which is going down. This is going to be 60 Newton. That's going to be 100 times 3 divided by 5. So you have two directions, and each one of them is going to create the moment. Then you have to think about, well, if I apply 80 Newton here, what is my perpendicular distance from this point O? We said you can extend the line of the action. So this is the line of action, and this is going to be the perpendicular distance, and that distance is going to be just 2 meters. So this is going to have 80 times 2 meters, and the unit for this one should be the Newton times meter. I forgot to mention about the moment has the unit. The unit is going to be force times the distance as the Newton times meter. And what is the direction of this moment? Well, this force tends to rotate about this way, and this is the clockwise direction. So we're going to put negative sign on this one here. Then you look at the y component. This is a 60 Newton, and the perpendicular distance is going to be, you extend the line of action. This is the perpendicular distance from the point O to the line of the action. So we're going to multiply it with a 5, and again this unit is going to be Newton times meter. And then let's think about what is the direction of this rotation. This force is also going to make this one turn this way, so it's going to be clockwise direction as well, so it's going to be minus as well. And this summation is going to be the moment with respect to the point of O. So the net moment is going to be minus 160 minus 300 Newton times meter, and that is equal to minus 460 Newton meter. And that is the net moment, and direction is going to be clockwise. The second example, we are going to use the vector product, which is the cross product. This is the case where you have 3-dimension. 3-dimension is hard to analyze in the scalar form because you have 3 components. Each one of the components you have to figure out what's the distance. So it's getting very complicated. It's better to use a vector form. And the vector form is that this is the vector form. You need to find out what is the precision vector R, and you also need to find out what is the force direction. And in this case, we have two different forces. We have force of 1, we have force of 2. They all apply to the same point A at here. So it's very easy for us to identify the position vector, which is from the O to this point of A. The force is given as a vector form already, so we don't need to figure it out. Sometimes they don't give you this, then you have to figure it out, like what we did in the previous chapters. So let's first find out what is the position vector of O. If you want to find ROA, we are going to use the position A minus position of O, where O is going to be 0, 0, 0. So what we need is to find out what is the position of A. And the A here, the component X, is going to be 4 feet. So we are going to have this one, which is going to be 4I, where the Y is going to be 5 feet to the positive. This is going to be positive 5J. And then Z direction is going to be this much, which is 3, and that's positive of 3K. So your ROA is going to be 4, 5, and 3. Now, we want to find a moment for two different forces, and these two forces, each one of them has different component, but they are applying to the same point. So we can actually first to sum these two forces together. That will simplify our calculation. And let's find what is the net force of these two. So by summing these two together, and you just sum the same component at the same direction. So 100 minus 200, we have a minus 100 of I. Minus 120 plus 250, we have positive of this minus that will be 130. And sum these two, that's 175. Okay, so now we have a force, we have a position vector. We can use this formula to find our answer, and we just use the determinant method. We put the I and J and K on the top. This will tell us the direction of the moment. And then we put the R component, which is going to be 5, 4, and 3. They are all positive. And then we put the force component. The first one is negative 100. Second one is 130. And the third one is 175. And be careful, it has a unit which is Newton times meter. And then you just find the determined result. Let's just see what the result looks like. So here it's the same as we showed you before. When you do this calculation, you're going to get the result is like this. Oh, it's well, it's not Newton times meter because we are using the US custom unit, which will be feet times pound. Okay, so if it's a SI unit, it will be Newton times meter. And for the US customs system, we have the pound times feet or feet times pound. And that is the result of this moment. Before we finish this video, I wanted to give you a quick ad here. So it just kind of a test your understanding about the concept of the moment. So let's say we have a force with a magnitude of F, and apply in a 4 different two-dimensional configuration. So it's a P, Q, R, and S. And select the case result in the maximum and the minimum torque value to the knot. If you actually use a torque wrench and you wanted to turn this bolt here, and you apply a force, you have an option to use the P, Q, R, and S. If you apply the force at S direction, which is just along the line of the lever arm, you are not going to create any of the tendency for this one to rotate about in this direction. Because if you wanted to create a moment, you need to have a perpendicular distance where you extend the line of the action, and the reference point is going to have a 0 perpendicular distance from your line of action. However, if you apply the force in the q direction, your line of the action is this one here, and this point is going to have this much of the distance to be your line, to be your lever arm. So this one create the maximum of the moment. So Q is going to give you the maximum. This one and this one will have partial of the moment, but it's not as stronger as the Q, where the S is going to be the minimum, which is going to be 0. So the answer for this one is the Q and S. All right, so this is the end of the first part. We have more to talk about in the next video. I'll see you soon.